Hi, this is Rafael from the Champalimaud Center for the Unknown, and I will have the pleasure to open the session focused on key space trajectory imaging. The first talk of the session was supposed to be given by Levi Kerkela from the University of College London. However, due to some unexpected issues, he couldn't make it today. However, he will try to be present during the Q&A questions so he can answer directly your questions during that session. So I will give this talk in his behalf, and I hope you enjoy. So in the next 45 minutes, I'm dividing this talk in three parts. First, I will introduce you what is key space trajectory imaging, or QTI for short. Then I will show you what we have done so far in Dipy to reconstruct data from QTI. To note that the implementations of the code that I will show today was led by Levi. And on the last part of my talk, I will take some minutes to also show some of my own work on advanced diffusion encodings. In particular, I will be discussing the correlation tensor imaging framework that uses double diffusion encoding to more generally resolve sources of non-Gaussian diffusion or kurtosis. Okay, so let's get started. Just a recap. So far during this workshop, we have been discussing different strategies to characterize diffusion MRI data acquired with conventional diffusion MRI sequence, the pulse gradient spin echo sequence that I'm showing here. This pulse sequence contains two diffusion gradient pulses to basically probe diffusion across a single direction in the B value. This is the reason why this sequence sometimes is referred to as single diffusion encoding, or SDE. In key space, the SDE sequence is equivalent to sampling a point for a given key value. To note also that in the single diffusion encoding, the second pulse pair is applied after a 180 degrees RF pulse. So this will have an opposite effect than the first gradient pulse. So for the sake of simplicity, during this talk, two opposite gradient waveforms will be used to present the single diffusion encoding sequence like the schematic that I'm showing here. So after acquiring several data points for different B values in gradient direction using this sequence, we can then apply the two types of models that we discussed on the previous talk. As a summary, phenomenological models that characterize signal properties without postulating hidden mechanisms, and microstructure models that tries to directly relate diffusion-weighted signals to tissue properties. However, due to the finite information provided by single diffusion encoding, both model types can have limited specificity to provide a complete characterization of changes in health and disease. So a central question on diffusion MRI development is how we can obtain more information to improve our diffusion MRI models. A strategy to obtain more information on tissue diffusion is to move from the signal diffusion encoding to multidimensional encodings or encodings from key trajectory imaging. So what is key trajectory imaging? So instead of acquiring image after applying single directions and magnitudes as done in the single diffusion encoding, key trajectory imaging consists in acquiring signals after probing diffusion at multiple directions. This can be done by, for example, applying two diffusion encoding blocks before acquiring the diffusion data. Each of these diffusion blocks can probe different magnitudes and directions. So they have independent directions and magnitudes as shown here in the key space image. We can also apply a triple diffusion encoding. So this basically applies three different encoding blocks with independent directions, and this can be used to probe all three special directions simultaneously. Alternatively, we can also use the key trajectory planar encoding, which use a continuous diffusion gradient waveform to try to map directions across different diffusion across different directions. So for example, in this trajectory that I'm showing here is trying to acquire two directions simultaneously or a plane. And we can also design continuous waveforms to probe all the directions simultaneously. So here in this trajectory is trying to capture an isotropic information of diffusion. Now the question is how to summarize the information captured by all these multiple gradient waveforms. In 2014, Wesson and colleagues proposed the B-tensor valued framework that characterized the information of the different key trajectory encodings in a common way. Basically, he demonstrated that if we assume that tissue can be represented by a sum of a general number of multiple Gaussian components, it is enough to characterize the different gradient waveforms by its B-tensor. So in opposite to the SDE sequence that could be characterized by just a gradient intensity in direction, key trajectory sequence need information of the full B-tensor, which can be visually inspected by an ellipsoid. To illustrate the B-tensors for different gradient waveforms, let's go back to my previous slide and plot the B-tensor ellipsoid geometries for the different sequence. As expected, the B-tensor for the SD sequence will have a stick geometry. Both double diffusion encoding and key trajectory planar encoding will show a planar B-tensor. Both triple diffusion encoding and key trajectory spherical encoding will probe all diffusion directions simultaneously, so therefore it will show a spherical or isotropic B-tensor, shown here. To have an intuition on the different information provided by the different B-tensors, let's give a look to the following toy models or voxel case scenarios. First, let's consider a voxel containing equal-sized spherical components. For example, this could correspond a simple representation of a system with spherical cells. Second, let's consider a system containing spherical components but with different microscopic sizes. Third, a system comprising random-oriented sticks components with constant shape and size. And last, a system containing random-oriented components with different shapes and sizes. Now, let's look to the different log signal decays for each case produced by each B-tensor. For the first case, since a system is comprised by spherical compartments, diffusion is isotropic, and thus the measured signal for all sequences is the same, independently to the directions that they are measuring. Since the spherical compartments all have the same sizes, all sequences will show a linear decay with a B value. In the second case, diffusion is still isotropic, so all sequences still provide the same information. However, now all sequences show a deviation from the linear relationship between the log signal and the B-tensor magnitude. As explained yesterday on QTI talk, this deviation is caused by the presence of diffusion heterogeneity across the spheres with different sizes. This deviation can be quantified by a diffusion kurtosis term, which here is referred to K-iso, since the diffusion isotropic variance is causing this kurtosis term. For the third case, things get more interesting. So in global, diffusion is still anisotropic because the components are random oriented. However, if we apply a single direction, the single directions will probe different apparent diffusivities because the angle between the linear gradient direction and structure orientation will be different from component to component. The measured signal will therefore show a deviation from the linear decay. And this is because of a kurtosis term associated to the local microscopic anisotropy variance, reason why I will call this kurtosis term as K aniso. However, the isotropic component since it's probing all directions simultaneously, will be sensitive to the mean diffusivity of all the components, which is constant because the size of these microscopic components is a constant. So its measure signal will be sensitive to K and ISO and will show a linear decay. The difference between the measurements of linear and spherical encoding will basically give the information of K and ISO. In the system containing both variants in compartment size and shapes, the linear encoding will be sensitive to both types of variants. So we will be sensitive to a total kurtosis. However, the isotropic encoding will only be sensitive to the isotropic kurtosis source. And thus the difference between the two experiments will give the information of the amount of anisotropy, microscopic anisotropy, or K and ISO. The deviation from the data measured by the isotropic encoding from the linear decay will reveal the information of K-ISO. For the planar encoding, the information that this will capture will just be intermediate case of the linear and the spherical encoding. So a general expression that can relate the different encodings with a different kurtosis source is given here. In this expression, we can see that the amount of the sensitivity to K and ISO is given by this new parameter B delta, which reflects the shape of the B tensor. From this expression, you can note that to resolve this equation, we need at least two B-tensor shapes and two B-tensor magnitudes. We can also generalize this equation to a three-dimensional anisotropic system. In the previous slide, I was only considering case of isotropic or random-oriented components. However, we know that tissue can have some degree of alignment, as in white matter. So a more complete expression for QTI is expressed here. From this expression, we can estimate the total diffusion tensor, basically the tensor of DTI, together with the covariance tensor, which is a 3 by 3 by 3 by 3 matrix with 21 unique elements. From this tensor, we can calculate the QTI unique parameters, such as K-ISO and K-aniso estimates. It is important to note that from this equation, we actually need to input the full 3 by 3 B-tensor matrix. Sometimes, our scanners only provide the information of the main direction, magnitude, and shapes of the B-tensor. However, this is not a problem for us because our codes can automatically reconstruct the full tensors using this expression. If you got a bit lost with the theoretical aspects on the last slides, the key points to keep in mind is just the use of a QTI can provide unique information, and basically this is first based on the assumption that tissues can be represented by multiple Gaussian component assumption, and then we can extract unique information, as for example the anisotropic kurtosis, which reflect the degree of microscopic anisotropy of the system. So basically this is equivalent to aligning all the microscopic systems to a common direction and characterize its anisotropy. We can also decouple things as the isotropic kurtosis, which will reflect the variance of different sizes of the components. Also, to have an intuition of the value of this approach, I'm just showing here an example of the application in tumors. So, for example, if we want to distinguish different types of tumors, as a meningioma and glioblastoma, this in histology have very different characteristics. So, for example, while in the meningioma, this contains cells, elongated cells that are random oriented, in the glioblastoma, we have more isotropic cells with different size variants. If we look to the total kurtosis, we will see that the contrasts are similar, so we cannot distinguish these two types of tumors. However, if you decouple kurtosis in different sources, you can see that from the KNI anisotropy that the meningioma shows high anisotropic sources, which is in line to the high anisotropy of the cells of the meningiomas, while in the glioblastomas, the K-aniso will be close to 0. Looking to K-iso, since the cells have uniform sizes, the K-iso will show low contrast on the meningioma and high contrast on the glioblastoma, which has a higher variances on sizes. Another thing that is important to note is, although here in this talk I focus more on the use of QTI on distinguish different kurtosis sources, this tensor allows the extraction of other several measurements. So here are just some examples that are on this following paper. Due to time constraints, I will not have the time to explain all the different contrasts. However, just to highlight that one thing that we can extract is, for example, what many studies are trying to address, which is a microscopic fraction anisotropy, which is basically an index of anisotropy that is normalized from 0 to 1, which 0 corresponds to isotropic systems, while values close to 1 corresponds to anisotropic systems. So, for example, in the regions of the white matter. So the microscopic FA is equivalent to the FA, but it doesn't have the dependence on the crossing fibers. So, for example, we see that here the microscopic FA will have even higher values on regions that are crossing. However, since it's white matter, it still contains well elongated cells. So saying this, now it's time to show the QTI implementations in Dipy. I will make a break here, so I will see you in the next video. Thank you for your attention.